For over a century, we have believed in a simple story, that the universe began with a single explosion, the Big Bang, and from those primordial fragments, stars and galaxies slowly formed over billions of years. However, when the James Webb Space Telescope looked back into the past, to a time when the universe had only just been born, it discovered something unsettling. Enormous galaxies, fully developed and disturbingly complete. They are too large, too old for their age. Their existence is like walking onto a construction site and finding a solid, finished tower before the foundation has even been laid. This has pushed the scientific community into a quiet crisis, because if what we are seeing is real, then humanity's entire understanding of how the universe began may be fundamentally wrong. This is not a distant speculation. It is a warning from Roger Penrose, a Nobel Prize winning physicist. Based on raw data from James Webb, he is gradually revealing a chilling possibility, that the universe may not have begun from nothing. Instead, what we are seeing could be the lingering ghosts of a world that existed before the Big Bang itself. In this journey, we will not only decode what James Webb has observed, but also follow Roger Penrose into one of the most controversial ideas in modern science, the possibility that a universe existed before ours. And in understanding that, you may begin to redefine your place within the endless cycle of space and time. If you are drawn to uncovering the truth behind the vast darkness of the cosmos, you can subscribe to Space Lull to continue exploring with us. And now, get ready, because we are about to step into an entirely different era. To understand why the discoveries made by the James Webb Space Telescope are so deeply unsettling, you and I need to look directly at the deity we have quietly trusted for over a century, the Big Bang Theory. We often begin stories with the phrase, "once upon a time." But in cosmology, that phrase has a more precise name, the Big Bang. Over the course of modern scientific history, we have come to assume that 13.8 billion years ago, there was a moment when everything emerged at once from nothing. We call that moment the beginning. But have you ever paused and asked yourself, why are we so certain that this was the beginning? Is it a proven truth, or simply a label we've placed on something we do not yet fully understand? When we hear the term Big Bang, most of us imagine a massive fireball exploding into a dark, empty space. You might picture matter being thrown outward in every direction from a single central point. But the truth is, there was no explosion, and there is no center. The Big Bang is, in fact, a term used to describe the expansion of space itself. Imagine space as the surface of a balloon that is being slowly inflated. Galaxies are not moving through space. It is the space between them that is stretching and expanding. According to data from the Planck satellite of the European Space Agency, along with measurements from NASA, this expansion has continued for 13.8 billion years. That number defines the age of the universe, based on calculations that trace time backward to a state where everything appears compressed into an extremely small, extremely hot point. However, there is a common misunderstanding, even among those who love science. We tend to assume that this singular point is the starting line. What scientists rarely say directly is this: our physical equations only remain valid for a very brief moment after the expansion begins. When we attempt to use mathematics to look deeper, toward the exact moment of zero, everything breaks down. The numbers diverge toward infinity. Time and space lose their meaning. In other words, modern science can only confidently say this: the universe was once extremely hot and extremely dense, and then it began to expand. As for what happened at the exact first moment, or whether there was even a true first moment at all, we do not yet have an answer. We assume the Big Bang is the beginning not because we have proven that nothing existed before it, but because it is the furthest boundary we can observe. We treat it as the edge of knowledge. But what if that edge is only a veil? For decades, the cosmic microwave background, the faint afterglow of light remaining from shortly after the Big Bang, has been considered strong evidence supporting this model. It is the oldest map we have of the universe. But within that map, thinkers like Roger Penrose have noticed subtle irregularities, patterns that, according to standard Big Bang theory, should not be there at all. If the universe were a house, then the Big Bang would be like a massive fire that erased all traces of previous occupants. You and I step into that house, covered in ash, and conclude that its history begins with the fire. But now, the James Webb telescope is beginning to dig beneath that layer of ash, and what it is uncovering are structures so large, so refined, that they appear to have been built before the fire ever began. This question is not only for physicists in laboratories, it is for all of us. Because if the Big Bang is not the beginning, then the idea of linear time, past, present, and future, which you use to measure your own life, may be nothing more than an illusion. Our universe may not be a straight line moving from point A to point B. It may be a loop, a rhythm, an eternal cycle of what has been and what will be again. So let me ask you this. If the Big Bang is not the beginning, what truly lies beyond that darkness? Are the massive galaxies observed by James Webb the final survivors of a forgotten era? To find out, we first need to understand the true power of the eye that allows us to look back in time. To understand why we are now being forced to reconsider the entire history of the universe, you first need to understand the tool that has pushed humanity into this moment of uncertainty. The James Webb Space Telescope is not simply an expensive camera floating in orbit. It is, in a very real sense, a time machine. But there is a paradox that few people fully realize. When James Webb looks deeper into space, it is not seeing what exists there right now. It is looking into a past that was already gone long before you were born. Let's pause for a moment and take this in. Light, the fastest thing in the universe as we know it, still has a limit. It travels at about 300,000 kilometers per second. For nearby distances, like the Moon or the Sun, this delay is almost unnoticeable. But when we talk about distant galaxies, light takes billions of years to cross the vast emptiness before it finally reaches your eyes, which means that when James Webb captures light from a distant galaxy, it is reading a message that was sent 13 billion years ago. That galaxy may have already faded, collided, or disappeared entirely, yet its image has only just arrived in front of you. You see, we are not observing the universe as it is. We are observing its history, and the history that James Webb is now revealing does not resemble any version we have written before. Before Webb, there was Hubble Space Telescope, the undisputed king of space observation. Hubble changed the world by showing us breathtaking images of nebulae and galaxies. But Hubble had a fundamental limitation. It observed the universe primarily in visible light, the same kind of light your eyes can detect. And the universe is not a clean, empty place. It is filled with dust and shaped by expansion. As we discussed earlier, the universe is expanding. And because of that expansion, light travelling from ancient galaxies gets stretched along the way. Like a spring being pulled apart, its wavelength becomes longer, shifting from visible light into the infrared spectrum. This effect is known as redshift. Hubble, which is sensitive mainly to visible light, is almost blind to these faint infrared signals, and so it left us with a deep darkness in regions where the first stars were expected to appear. James Webb was built to solve exactly this problem. With its massive 6.5-meter mirror, nearly 3 times larger than Hubble's, it can collect far more light. But more importantly, it sees in infrared. It allows us to look through thick clouds of cosmic dust and into regions that once appeared completely empty. In scientific terms, distance and age are often measured using a value called Z, the redshift index. Hubble could observe up to about Z equals 10, corresponding to a few 100 million years after the Big Bang. But those images were often faint and uncertain. James Webb has pushed far beyond that limit. It has reached Z equals 12, Z equals 13, and even further. It allows us to observe the universe when it was only about 2 to 3% of its current age. But it is precisely at this boundary that something strange begins to appear. According to the Standard Model, the early universe should have been chaotic, filled with primordial gas and tiny galaxies just beginning to form. We expected to see the infant stages of galaxies, but James Webb is showing us something else. Galaxies that are far larger than expected. Objects that already contain enormous numbers of stars, with structures that appear fully developed, as if they had already undergone billions of years of evolution. At this point, scientists are forced to confront a difficult possibility, one that you may already be sensing yourself. Either our calculations of how quickly stars and galaxies form are incorrect, or the light Webb is receiving did not begin from zero after the Big Bang. There is a moment in cosmic history known as the cosmic dawn, when the first stars are believed to have lit up the darkness after hundreds of millions of years. James Webb was sent to witness that moment. For us. But instead of seeing the first light of a beginning, it seems to be showing us something else, something that was already there. James Webb has taught us something very simple, but very important, a lesson in humility. We believed we had built a tool powerful enough to see everything, but in reality, we are discovering that the past is far more complex than we imagined. Each time Webb sends back new data, with higher redshift values, another wall appears in front of us. We are looking at history, a history filled with objects that should not exist. And if those galaxies are too large and too old for such a young universe, then the timeline we have trusted may be missing something essential. So let me ask you this. If space and time did not begin from zero, then what are these massive galaxies, really? Are they simply young structures that grew at an impossible speed? Or are they the last survivors of a world that came before? To find the answer, we now have to face these rule breakers directly. The galaxies so large that they are forcing us to tear apart the pages of our old textbooks. Have you ever experienced that moment when you felt completely certain about something, only for a single piece of evidence to appear and quietly unravel your entire understanding of the world? That is exactly what the astronomical community is going through right now. And the cause comes from a group of objects now referred to, almost defiantly, as universe breakers. Let's return for a moment to the timeline we discussed earlier. According to the standard Big Bang model, the early universe was a very simple place. After the initial expansion, the universe needed time to cool down, time for gravity to gather clouds of hydrogen and helium, and only then could the first stars begin to form. Scientists estimate that it would take billions of years for those stars to assemble into large, structured galaxies like our own Milky Way. But when you and I look through the lens of the James Webb Space Telescope into the deepest regions of space, corresponding to a time just 300 to 500 million years after the Big Bang, we are confronted with something entirely different. In that distant epoch, Webb has captured images of 6 massive galaxies, and to help you grasp their scale, each of these galaxies contains billions of stars, with masses comparable to our Milky Way today. Now pause for a moment and think about that. Our Milky Way has taken over 13 billion years to evolve, collide, and accumulate enough matter to reach its current size. And yet, James Webb has found giant counterparts, existing when the universe had lived through less than 3% of its total history. To make this easier to imagine, picture yourself arriving at a construction site on the very first day of building. You would expect to see piles of dirt, scattered materials, and a few machines just beginning to lay the foundation. But instead, you are greeted by a fully completed skyscraper, bright, functional, already filled with people living inside. It is a contradiction, almost difficult to breathe through. According to the most advanced computational models of cosmic structure formation, the amount of ordinary matter at that time was simply not enough. Not enough gas, not enough dust, and most importantly, not enough time for gravity to shape something so immense. At this point, a question may naturally arise in your mind. Could James Webb be mistaken? At first, scientists hoped that might be the case. They considered the possibility that these were supermassive black holes, shining so intensely that we were misinterpreting them as entire galaxies. or perhaps cosmic dust had distorted the measurements. But as the data was analysed and reanalyzed, as errors were gradually ruled out, the reality remained unchanged. These galaxies are real, they are mature, they are massive, and they do not align with any scenario we have ever constructed about the beginning of the universe. Their existence leads to a critical insight. The early universe may not have been as young as we once believed. Its structure appears to have been developed from the very beginning. So what created them so quickly? Was there some unknown mechanism that accelerated star formation hundreds of times beyond our expectations? Or, as suggested in the hypothesis of Roger Penrose, which we will explore in more depth later, perhaps these galaxies were never built from the ashes of the Big Bang at all. There is a possibility here that may feel quietly unsettling. These objects may not have formed after the Big Bang. They may be structures that survived a transition from a universe that existed before ours. Like ancient islands, remaining after a great flood, standing still as the next generation tries to reconstruct history from scattered debris. James Webb is not only showing us beautiful images, it is presenting us with something else entirely, a kind of cosmic crime scene, one where the evidence seems to suggest that the true culprit may be the limitations of our own understanding. We may have been too confident in a one-directional model of time, and if the presence of these galaxies already feels difficult to accept, then you may want to prepare yourself. Because in the next chapter, we will see that it is not only the structure of matter that is in question, but even the clock we use to measure the expansion of the universe appears to be running incorrectly. Because the contradiction is not only in what we observe, it lies within the very way the universe is growing, moment by moment. And this discrepancy is so significant that it may be pointing towards something far deeper, that the universe itself may have had a hidden beginning, one that none of us has ever truly seen. Have you ever used two different clocks to measure the same period of time, only to find that the results differ so much that they cannot be ignored? That quiet sense of confusion is exactly what some of the world's most accomplished physicists are now experiencing. They call it the Hubble tension. And it is important for you to understand, this is not a minor calculation error. It is a structural crack in the very foundation of the knowledge we have been building for over a century. Let's begin with something simple. The universe is expanding. You already know this from earlier. But the real question is, how fast is it expanding? To answer that question, scientists use a value known as the Hubble constant. You can think of it as the speed of the cosmic vehicle that all of us are travelling on. And to measure it, we have developed two completely different approaches. The first method is to look at the universe's birth record. Scientists use data from the cosmic microwave background, CMB, the oldest light remaining from shortly after the Big Bang, which you encountered earlier. By analysing the tiny fluctuations in that ancient signal, our mathematical models predict that the expansion rate of the universe is about 67 kilometers per second per megaparsec, kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, galaxies move away from each other at a speed of 67 kilometers per second. Everything seems logical. Everything fits neatly within the Big Bang framework, until we apply the second method. The second approach is direct measurement, using modern rulers. Instead of looking at ancient data, astronomers observe supernovae, brilliant stellar explosions, and gravitational lensing in the present-day universe. And this is where things begin to shift, because the result is consistently different. It is not 67, it is 73 kilometers per second per megaparsec. Now, take a moment and look at the gap between those two numbers. A difference of 6 kilometers per second may seem small, but in cosmology, it is like measuring your own height and getting two results. One says you are 1.70 meters tall, the other says 1.85. This is not a rounding error. It is too large to be explained away by technical limitations or cosmic dust. At this point, scientists hoped that the James Webb Space Telescope would act as a kind of referee. They thought, perhaps Hubble made a mistake. Let Webb measure it again. But the results from Webb did not resolve the tension. They deepened it. Webb confirmed that the value closer to 73 is correct, which leads us to something far more unsettling. It is not that we misobserved a few galaxies. It is that our entire measurement system may be incomplete. If both sets of data are correct, the early universe pointing to 67 and the present universe pointing to 73, then something significant must have happened in between, something we do not yet understand. To make this clearer, imagine a child who weighs 3 kilograms at birth. Based on normal development, you would expect that child to weigh about 30 kilograms at age 10. But when you measure them at 10 years old, they weigh 50. Clearly, something else has influenced the process, something that was never accounted for. In physics, that something could be a new form of dark energy, or an unknown force that has accelerated the expansion of the universe beyond our expectations. But there is another possibility, one that is more difficult to accept, and I want you to consider it carefully. What if our measurement is wrong because our assumption about the starting point is wrong? Think back to what Roger Penrose suggested. If our universe is not a singular beginning, but a continuation from something before, then the expansion we are measuring may not originate solely from our Big Bang. It could be a residual motion, an inherited momentum from a previous cycle. The Hubble tension may be telling us something very important, that our current model of the universe is becoming too narrow, too constrained to fully explain what we are now observing. And when the way we measure reality begins to fail, that is when you know we do not simply need a better telescope. We need a different theory. At this point, the problem is no longer just about universe-breaker galaxies. Now, space and time themselves appear to be breaking their own rules right in front of us. So if our current system cannot explain the rate of expansion and cannot explain the early appearance of massive galaxies, where do we look next? Perhaps the answer lies in something even more fundamental than matter. Something we often take for granted. Light. A form of light that, according to our current theories, should never have been able to escape so early. Why would a universe that was once filled with dense, obscuring fog become illuminated so quickly? To understand that, we need to explore one of the most mysterious periods in cosmic history, the epoch of reionization. A time when light began to do things that science had never predicted. Let me ask you something. How would you see a flashlight through a fog so dense that light cannot pass through it? The usual answer is simple. You can't. And yet, in the early universe, the James Webb Space Telescope appears to be seeing exactly that. Let's move back in time, to a period scientists call the Dark Ages. After the Big Bang, the universe was not bright, as you might imagine. Instead, space was filled with a thick fog of neutral hydrogen, and this fog had a very specific property. It absorbed and scattered nearly all ultraviolet light from the first stars. To put it simply, the universe at that time was like a dark room filled with smoke. No matter how small the flame, a match, a candle, its light would be swallowed almost immediately. According to the theoretical models we have trusted for decades, it should have taken hundreds of millions, even billions of years for stars and galaxies to produce enough radiation to clear this fog, to transform neutral hydrogen into ionized hydrogen. This process is known as the cosmic reionization. But once again, James Webb presents a challenge to those long-standing assumptions. Webb has observed a galaxy known as JADES-GS-Z11. It existed around 330 million years after the Big Bang. At that time, the universe should still have been deep within that dense hydrogen fog. And yet, James Webb detected a remarkably clear signal: Lyman alpha radiation. I want you to focus on this detail. Lyman alpha radiation is a very specific type of ultraviolet light emitted by excited hydrogen, and it has a crucial property. It is extremely sensitive to neutral hydrogen fog. Even a small amount of that fog would block it completely. And yet, James Webb observed it shining clearly, from a distance of 13.4 billion light-years. Now imagine the reaction of astronomers. It is like standing in a stadium filled with smoke and still being able to clearly see the light of a small candle from miles away. This can only happen if the fog had already been cleared, long before. And here is the key insight. The universe did not just form earlier than expected. It became transparent, far sooner than any of our models predicted. So the question becomes, why did the fog disappear so early? If there was not enough time for the first generation of stars to accumulate sufficient energy, then what removed the darkness? There are two possibilities currently being considered. The first is that the earliest stars were far larger and far hotter than we have imagined, so powerful that they burned through the surrounding space almost instantly. The second possibility involves supermassive black holes, those immense structures we mentioned earlier. They may have formed extremely early and released enormous amounts of energy, tearing through the cosmic fog. But there is a third possibility, a more difficult one to accept, and one that Roger Penrose has suggested. What if that fog had already been partially ionized before our Big Bang even began? If the universe operates as a cycle, then the energy from the end of a previous universe may have left behind thermal scars, regions of space that were already transparent from the very beginning. In that case, the light from JADES-GS-Z11 is not struggling to escape the darkness. It is travelling along a path that had already been cleared. Now, you may begin to notice a pattern. The galaxies are too large. The expansion is too fast. The light escapes too early. All of these observations are pointing in the same direction. The standard model, the rulebook we have been using to understand the universe, may be missing its most critical pages. We are trying to solve a problem with a set of assumptions that may no longer apply. Through James Webb, the universe seems to be sending a clear message. Do not see me as something newly born. See me as something being reborn. And if light can escape this early, if everything appears to operate at such an unexpected pace, then we are forced to ask a deeper question. What existed before light itself? What happened in that silent interval before the Big Bang that prepared the way for all of these contradictions? Because when we reach the limits of our current model, we begin to realize something else. We may only understand about 5% of reality. The remaining 95% remains hidden in darkness, a vast unknown that may contain answers about parallel universes and endless cosmic cycles still waiting to be discovered. Imagine trying to complete a 1,000-piece puzzle, but after decades of effort, you realize you only have 50 pieces in your hands. The rest are not just missing, they are invisible. That is exactly where humanity stands when facing the universe. There is something I want you to hold on to in this moment. Science is not wrong, but it may not be enough. For many years, scientists have built an incredibly refined model to explain everything, from how atoms form to how galaxies rotate. We call it the lambda-CDM model. Within this model, we confidently describe what the universe is made of. But when you look closely at the numbers, you begin to notice something both surprising and humbling. According to the standard model, about 68% of the universe is dark energy, the mysterious force driving the accelerating expansion we discussed earlier in the context of the Hubble tension. Another 27% is dark matter, the invisible glue that holds galaxies together and prevents them from drifting apart. So what remains? For you, for me, for the stars and galaxies that James Webb is observing? The answer is only about 5%. You heard that correctly. Everything we can touch, everything we can see, everything we can measure using light, everything that forms your body and the light of the stars accounts for just 5% of reality. The remaining 95% is an unseen, unknown darkness, something we can name but do not truly understand. In other words, we are trying to explain the entire universe using only 5% of the available information. It is like examining a single drop of seawater and attempting to describe all life in the deepest parts of the ocean. At this point, you may find yourself asking, if we only understand 5%, why have we trusted the Big Bang and our current models so completely? The answer is simple, because that 5% worked remarkably well until James Webb arrived. Before Webb revealed images of what could be described as adults in a nursery, our standard model explained the universe with impressive accuracy. But now, these new observations are pushing that 5% of understanding to its limits. When James Webb observes galaxies that are far too large for such an early moment in time, it is effectively telling us, the 5% you understand is no longer sufficient to explain what you are seeing. Perhaps dark matter does not behave the way we thought. Perhaps dark energy experienced a hidden phase of acceleration in the early universe. Or, there is another possibility, one that may feel more unsettling, that the unseen 95% may carry information or memory from another universe. Roger Penrose has suggested that what we call physical constants, or dark matter itself, may not be entirely new. They may be remnants. If the universe operates in cycles, then that 95% we do not understand could be the software left running from a previous system, still operating quietly within the hardware of our current universe. It is important for you to understand this. Science is not a collection of eternal truths. It is a process of continuous correction. The fact that James Webb is challenging our current models is not a failure of science. It is a gift. It frees us from the assumption that we already understand everything, and it forces us to acknowledge that behind the brilliant surface of the Big Bang, there may be deeper forces at work. At this point, you may begin to feel something else, a sense of scale. We are small. We exist on a small planet, looking outward into a vast universe and understanding only 5% of it. But it is precisely that lack of understanding that creates space for discovery. When this 5% model can no longer explain why galaxies grow so quickly, or why light escapes so early, that is when we must allow room for ideas that seem unconventional, ideas that extend beyond the boundaries of a single universe. So what if that 95% of unseen reality is not simply unknown matter, but a sign of interaction between our universe and something else? What if your universe is only a small bubble within an endless ocean of other universes? Because when 5% of understanding begins to break down, that is when we step into the next phase, a place where boundaries begin to dissolve, and the concept of the multiverse is no longer science fiction, but a mathematical possibility attempting to preserve our understanding of reality. Have you ever stood in front of a mirror and wondered whether somewhere out there another version of you is looking back, but from within a completely different world? The idea of the multiverse may sound like a waking dream, but for modern cosmologists, it may be the only key to explaining why the James Webb Space Telescope is observing massive galaxies so early in time. Perhaps our universe was never truly unique. It may be just a small part of something far greater. Imagine all of space as an endless ocean of energy. Within that ocean, Big Bang events occur continuously, like bubbles forming and expanding. Each bubble is its own universe, with its own physical laws. There could be universes where gravity is so strong that everything collapses instantly. Others, where light never turns on at all. And our universe, the bubble you exist within, just happens to have the right conditions for life to emerge. This idea is known as the bubble universe. But what does this have to do with the universe breakers that James Webb has discovered? Consider this. What would happen if two of these cosmic bubbles collided, or merged, in their early stages? This is where the hypothesis becomes more unsettling. Some researchers suggest that the period known as cosmic inflation, that rapid expansion shortly after the Big Bang, may not have been a random event. Instead, it could have been the result of our young universe being absorbed by a larger parent universe, or colliding with a neighbouring one. When such a collision occurs, it may not only transfer energy, it may also transfer matter. Think of it this way. Pouring a full glass of water into a nearly empty bowl, the massive galaxies observed by James Webb, those structures that appear far too mature, far too early, may not have formed from the ashes of our own Big Bang. They may be migrants, structures that originated in another universe and drifted into ours during that merging process. This would explain why we observe fully developed structures at what should have been the very beginning. They were not built here. They were already built somewhere else. At this point, you may be wondering, if this is true, could we find evidence of such a collision? The answer is, we may already have. Do you remember the Hubble tension? The differing expansion rates across regions of space may be the result of distortions created when two universes merged. Like ripples on the surface of water after a stone has been thrown. Even within the map of the cosmic microwave background, CMB, scientists have identified a massive anomaly known as the cold spot, a region of space that appears unusually empty. Some researchers believe this could be the bruise left behind by a collision between our universe and another. If this is true, it would completely change how you define home. The universe would no longer be a closed, isolated system floating in emptiness. It would be something else entirely, a structure that interacts, that exchanges, and perhaps even evolves within a much larger cosmic ecosystem. In that sense, James Webb is not only helping us look into our past, it may be helping us glimpse our neighbours. The overly bright galaxies, the early escape of light. All of these observations can be explained if we accept that our universe may be receiving energy from beyond itself. And yet, even though the multiverse is an elegant solution, it may not be the final answer, because the anomalies in the cosmic microwave background, the ones that Roger Penrose has pointed out, suggest something deeper still. The multiverse speaks of parallel spaces, but Penrose is speaking of something else, the continuity of time. So prepare yourself, because if this idea has taken you across space to search for neighbouring universes, then what comes next will take you across time, in search of something far more personal. What if your universe is not a random bubble in an endless ocean, but a single breath within an eternal cycle? What if the structures James Webb has revealed do not come from elsewhere, but from a before? Because after exploring the possibilities of space, we are about to encounter a mind that dared to challenge the Big Bang itself. Let us now step into the world of Roger Penrose, a man who believes that the death of a previous universe may be the very seed of our own beginning. Now, I want you to stand with me in front of a mind that dared to look all the way into the depths of nothingness and return with something even more unsettling. We are about to leave behind the idea of parallel neighbours and step into a perspective where time is no longer a straight line leading to an ending, but a circle without beginning or end. Let me introduce you to the central figure of this shift in thinking, Roger Penrose. Penrose is not someone who entertains speculative ideas lightly. He is the physicist who, together with Stephen Hawking, proved that black holes are an inevitable consequence of general relativity. And yet, this same man, who has spent his life studying the ultimate limits of space and time, is also the one who suggests the Big Bang we have trusted may only be a rebound from a far more distant past. His theory carries a complex name, Conformal Cyclic Cosmology, or CCC. But do not let the name distance you. Let's approach it in the simplest way possible. The insight Penrose offers is this. The universe does not have an absolute beginning. It has cycles. He calls each cycle an eon. Now imagine this. Our universe is expanding. Day by day, galaxies move farther apart. Stars will eventually exhaust their fuel and fade into darkness. In the distant future, the universe will contain almost nothing except supermassive black holes, the same dark giants that James Webb is now detecting. But even black holes are not eternal. According to Hawking radiation, over an unimaginably long period of time, a number so vast it would require a 1 followed by 100 zeros, Even black holes will slowly evaporate. Now try to picture the final state of the universe. No stars, no planets, no atoms. Only photons, particles of light without mass, drifting through a space that is completely empty. And this is where Penrose identifies something remarkable. You see, in a universe composed only of massless particles, the concept of scale disappears. There are no clocks to measure time, no rulers to measure distance. For these particles, an infinitely large universe and a space as small as an atom are indistinguishable. In other words, when the universe becomes empty enough and expands far enough, it loses its sense of size. And mathematically, that infinite, expanded state becomes equivalent to a new Big Bang. Penrose proposes that the extremely diluted end of a previous universe is identical, in form, to the dense beginning of our own. The Big Bang is not creation from nothing. It is a transition, a moment where one eon ends and another begins. At this point, you may be asking, what about the second law of thermodynamics? Doesn't entropy, disorder, always increase, leading inevitably to decay? This is where Penrose introduces one of his most profound ideas. He suggests that black holes act as entropy processors. As they consume matter, they also absorb disorder, and when they evaporate, the universe is left in an extraordinarily smooth, low-entropy state. This explains something crucial: why our universe began with such remarkably low entropy, a condition necessary for the formation of galaxies, like the ones James Webb now observes. Now, consider the connection. The galaxies that should not exist, the expansion rates that do not align. These may not be errors. They may be inheritance. If our universe is a new breath, then those massive galaxies may be among the first structures shaped by patterns left behind from a previous cycle. The universe did not begin on a blank page. It began on a page that had been erased. But not completely. Penrose believes that what James Webb is observing is not rapid, impossible growth, but something else entirely: a return. Does that thought create a quiet unease? If CCC is correct, then eternity is not a distant future. It is a loop that we are already inside. Every star you see, every atom in your body, may have participated in countless universes before this one, before coming together, here, in this moment. But Penrose does not stop at theory. He claims that the previous universe left behind measurable traces, imprints, that can still be detected today. These echoes of the past are hidden within the oldest light we have ever observed. So what would you think if the images from James Webb and the maps of cosmic background radiation did not only show our universe, but also revealed the remnants of something that came before? Because next, we will look for actual evidence. We will examine what are known as Hawking points, subtle thermal scars in the fabric of the sky. Marks that Penrose believes may be the strongest indication yet that we are not the first generation of this universe. Imagine you are looking at an image, capturing the aftershock of a great explosion. That is what the CMB map represents, the cosmic microwave background I mentioned earlier. It is the oldest light we have ever observed, emitted about 380,000 years after the Big Bang. For decades, scientists have treated this map as definitive evidence that the universe began from nothing. They saw near-perfect uniformity, with only tiny fluctuations in temperature, seemingly the result of random quantum vibrations. But when Roger Penrose and his collaborators examined the data from the Planck and WMAP satellites, they did not see randomness. They saw patterns. And here is the insight I want you to explore. The universe does not erase everything. It leaves behind thermal scars. Penrose calls these traces Hawking points. Let me explain why they carry that name. As we discussed earlier, black holes evaporate through Hawking radiation. At the final stage of a previous cosmic cycle, when a massive black hole completely evaporates, it releases an enormous amount of energy into a very small region of space. According to the CCC theory, when the transition between two universes occurs, this concentrated energy does not disappear. It becomes compressed through the Big Bang boundary and re-emerges in our universe as localized regions of unusual temperature. Try to imagine it this way. If you set off a powerful firework very close to a curtain, even if you replace the curtain afterward, the heat from the explosion may still leave a faint burn mark on the new surface. And this is where the story becomes more intense. Penrose claims that he has identified hundreds of these burn marks on the CMB map. They appear as circular regions with sizes roughly 8 times the diameter of the Moon, as seen from Earth. These are areas where the temperature differs noticeably from their surroundings, far beyond what random models would predict. At this point, you may be asking, why don't other scientists agree? Because the boundary between a true signal and statistical noise is extremely delicate. Many experts argue that if you examine enough data for a long enough time, you will always find patterns, much like looking at clouds and seeing the shape of a dragon. They describe this as the tendency to see what we expect to see. But Penrose remains firm. He argues that the probability of these thermal points appearing randomly is less than 1 in 125, a number significant enough to make any scientist pause and reconsider. Now, connect this idea with what James Webb is observing. Webb does not look at the CMB, it looks at galaxies. But if Penrose is correct about Hawking points, then these regions of excess energy could act as ideal nurseries. Higher temperatures and localized concentrations of matter could have accelerated star formation far beyond normal expectations. This may explain why James Webb observes massive galaxies so early. They formed in regions that already contained inherited energy from a previous universe. They did not begin from nothing. They began with an advantage, a kind of cosmic inheritance. If those circular imprints in the sky are truly the remnants of black holes that died trillions upon trillions of years ago, then we are living within a vast cosmic graveyard. Every star you see, every breath you take, may be part of an energy flow that has passed through countless previous universes. We are not the first. We are not alone emerging from nothing. We are continuations. In this sense, James Webb becomes something more than a telescope. It becomes a kind of microscope, revealing the genetic code of the universe itself. Each image it sends back is not just beauty, but evidence of an ongoing process of cosmic evolution. And when you begin to accept that we are not the first episode of the story of the universe, everything starts to feel more connected. The Hubble tension, the oversized galaxies, the early escape of light, all of them become pieces of a much larger picture, a universe that may not begin, but instead repeats. There is something we need to clarify before we go any further. Everything you have just heard, from galaxies that are too large, to mismatched expansion rates, to theories of cosmic cycles, is not only a matter of physics, it is a question of how we understand reality itself. Because if the data from the James Webb Space Telescope is accurate, and if what scientists like Roger Penrose are suggesting holds even partial truth, then it means this. We may be using a model that is too simple to explain a system far more complex. Let's think about this in a more practical way. For many years, we have become accustomed to viewing time as a straight line, a beginning, a process, and an end. That way of thinking is not wrong. It helps us build history, measure progress, and make decisions in everyday life. But in cosmology, that approach is beginning to reveal its limits. When you look at what is happening, galaxies forming too quickly, light appearing too early, expansion rates that do not align, it is like using an old map to navigate a city that has completely changed. This does not mean that everything we know is wrong. It simply means the current picture is incomplete. And this is the part that many people overlook. Science does not operate on absolute certainty. It operates through continuous correction, based on new data. James Webb is not destroying our knowledge. It is forcing us to upgrade it. And if you look at it this way, these discoveries are not something to fear. They are simply signs that we are moving closer to a more accurate model of the universe. But there is still a question you may be asking yourself. If the universe is not as simple as we once believed, if time is not entirely linear, what does this have to do with your life? The answer, in a very direct sense, is not much in the short term. Your daily life continues as it always has. Your work, your family, your decisions are not altered by the behavior of a galaxy 13 billion light years away. But on a deeper level, it changes how you see things. When you realize that we understand only about 5% of the universe, the rest consists of dark matter and dark energy whose true nature remains unknown. And even foundational models like the Big Bang are being reconsidered. Then one conclusion becomes clear. The certainty we often feel is only temporary. And that can be an advantage. Because when you are no longer bound to a fixed answer, you begin to think more flexibly. You accept that a system can be valid for 50 years and then require revision. An assumption can seem reasonable until new data appears, and a question can outlast any answer. That is exactly how scientists work. They do not begin with the belief that they are right. They begin with the assumption that something may still be missing. And if you look back at the entire journey of this video, you may notice a repeating pattern. When data does not fit, then we ask new questions. When models are insufficient, then we expand them. When limits appear, then we search for a way beyond. This is not only the story of the universe, it is how human understanding evolves. So instead of searching for a final answer to the question, was the Big Bang the true beginning? A more practical approach may be to accept that the question remains open, and that its openness is precisely what makes it worth exploring. If you look at it this way, what James Webb is showing us is not a contradiction that must be solved immediately, but a signal that there is more, beyond what we can currently see. And perhaps that is the most important realization, not where the universe began, but that we remain curious enough to continue exploring it. Because in a system as vast as this, the ability to ask the right question may be more valuable than having an answer. And if you are still here, listening to this moment, perhaps you have already realized that. We do not need to understand the entire universe to begin understanding it a little better, each day. And perhaps that is the most reasonable way to exist in a reality that is still being written. And so, after everything we have explored, from galaxies appearing too early, to models that no longer align, to theories that are reshaping how we understand the universe, something becomes clearer. It is not that we now understand the universe, it is that we are beginning to realize how much we do not. In science, that is not failure. In fact, it is often the beginning of progress. Because whenever data no longer fits the model, we are forced to look again and build something better. The Big Bang may still be part of the story, but perhaps it is not the entire story. Time may still flow as you experience it each day, but on a larger scale, it may behave in ways we have never encountered. And that does not complicate your life. If anything changes, it is your perspective. When you understand that what you know today may be revised tomorrow, you begin to see the world differently, less absolute, less hurried in reaching conclusions. And in a very real sense, that is how science works. Not by always having answers, but by remaining willing to ask new questions. So instead of seeking a final conclusion about the universe, perhaps it is more meaningful to accept that some questions will always remain open. And that openness is what makes the journey worth continuing. Tonight, as you lie there, in the quiet familiarity of your space, everything around you remains the same. The room, your breathing, the stillness. And yet, perhaps the way you see time and your place within the universe has shifted, just slightly. You do not need to understand everything. You do not need an answer right now. only to recognize that you are living within a reality that is still being explored, moment by moment. And if you are still listening, then perhaps you have already become a part of that journey. Let these thoughts slowly drift, like galaxies moving through the vastness of space, without urgency, without a fixed destination, simply continuing. And if tonight you have not yet fallen asleep, that is all right. At least you have travelled a little further in the way you understand the universe, and in the way you understand yourself. Tonight, if you look up at the sky and choose one of the faintest points of light, take a moment to realise something extraordinary. The light you are seeing may have begun its journey long before humanity ever existed. We often take pride in the fastest spacecraft we have ever built, moving at speeds of over 17 kilometers per second. But in this vast, dark ocean, that speed feels like a slow step, almost insignificant. If you had begun a journey at the moment our ancestors first drew on cave walls, travelling through thousands of years of history up until this very second, you still would not have covered even 1,000th of the distance to the nearest neighbouring star. The true vastness of the universe is not in the numbers that make us feel small, but in something deeper, that no matter how far the distance, we continue searching for a way to reach it. Right now, the Voyager 1 is still sending back faint signals from more than 24 billion kilometres away. And far beyond that, the latest observations from James Webb Space Telescope in 2026 are opening doors to ancient cosmic structures, places where reality itself begins to blur into the unimaginable. Welcome. This is Space Lull. We believe that every number out there, no matter how cold or distant it may seem, carries a story about where we come from. Stay with us, not just to measure the universe, but to feel the quiet connection between this small, beating heart and the vastness beyond. And if you find a sense of calm in journeys shaped by knowledge and wonder, consider joining Space Lull. Let's begin. Part 1. The Solar System, the Pride of Empty Spaces. Let us begin our journey from the most familiar place, our home. In textbooks or the visual models you often see online, the solar system appears crowded and vibrant. Planets glow brightly, placed close together, orbiting a radiant yellow sun. But the truth is, every one of those images is misleading your eyes. If a model were drawn to scale, the planets would be so small you wouldn't be able to see them, and so far apart that the distances would feel almost unreal. At its most fundamental level, the universe is not made of matter, it is made of emptiness. At the centre of that emptiness lies the sun. Imagine it as something vast and insatiable. It contains about 99.8% of the total mass of the entire solar system. Everything else, from massive gas giants like Jupiter and Saturn to microscopic dust, and even us, accounts for only the remaining 0.2%. Scattered remnants left behind after the formation of that star. If we shrink the sun down to the size of a basketball, our Earth would be nothing more than a tiny grain of sand sitting about 25 meters away. Neptune, the most distant planet, would be a speck of dust more than a kilometer from that basketball. And the space in between? There is nothing there. Only darkness and a silence so complete it feels absolute. We often think of the distance between Earth and the Sun as something immense, about 150 million kilometers. Astronomers call this 1 astronomical unit, or AU. To make it more relatable, if you were driving a car at 100 kilometers per hour without ever stopping, it would take you around 170 years to reach the Sun. And yet, in the scale of the universe, 1 astronomical unit is barely a single step. As we move beyond the warm region of the inner planets and past the asteroid belt, space begins to stretch in a way that feels almost unsettling. By the time we reach Neptune, we are already about 4.5 billion kilometers away from the Sun. At that distance, the Sun is no longer a glowing disk warming your skin. It shrinks into a sharply bright, distant point, cold against the black sky. Even light, the fastest thing in the universe, takes more than 4 hours to travel from the Sun to this frozen world. But Neptune is not the end. Many people assume that once we pass the planets, we have left the solar system. In reality, we are only standing on the front step of our home. Far beyond the orbit of Pluto lies the Kuiper Belt, a region filled with icy bodies and dwarf planets drifting in perpetual darkness. And even farther still, surrounding everything, is the Oort cloud, a vast spherical shell containing trillions of icy objects, marking the outermost boundary where the Sun's gravity can still hold on to something. The Oort cloud may extend as far as 100,000 astronomical units, nearly 2 light-years. If you stood at its outer edge and looked back toward the centre, our Sun, the source of all life on Earth, would appear as just another ordinary star, no brighter, no more remarkable than millions of others scattered across the Milky Way. Out there, the idea of day and night no longer exists. There is only existence itself, suspended in the void. And the farther we travel, the clearer a paradox becomes. The solar system is not defined by its planets, but by the vast spaces between them. Spaces so immense, so deep, that they seem capable of swallowing human imagination entirely. Matter is rare. Emptiness is the rule. We are living on a small fragment, drifting in an ocean of space so vast that our presence within it feels almost improbable. Pause for a moment between these billions of kilometers and distant regions we've just crossed. Can you feel that silence? When you look at the structure of the solar system and see Earth as nothing more than a colourless grain of dust within the immense reach of the Oort cloud, do you still feel that we are at the centre of something grand? Or are we simply fortunate enough to have found a warm place to rest in an endless, silent desert of space? Part 2. Light, the measure of time and space. As we leave the outer boundary of the Oort cloud and move into interstellar space, familiar units like kilometres or miles begin to lose their meaning. They become too small, like trying to measure the distance between continents using the length of a grain of sand. To truly understand the scale of the universe, humanity had to rely on something far more fundamental, something woven into the fabric of reality itself. Light. Light is the fastest thing in the universe. In a vacuum, it travels at approximately 300,000 kilometers per second. To put that into perspective, in a single blink of an eye, light can circle the Earth about 7.5 times. If you could move at that speed, you would reach the moon in just over 1 second. On Earth, light feels almost instantaneous. You turn on a lamp and the room is illuminated immediately. But once you step into the vastness of space, that incredible speed begins to reveal its limits. Light is no longer instant. It becomes something else, a patient traveller moving steadily across immense darkness. The distance from the Sun to Earth is about 150 million kilometres. Light takes 8 minutes and 20 seconds to make that journey. This means that if the Sun were to suddenly disappear right now, you would still see it shining in the sky for more than 8 minutes. We never see the Sun as it is in the present. We only see it as it was a few minutes ago. Because the universe is so vast, scientists use the distance light travels in 1 year as a standard unit of measurement, called a light year. Despite its name, a light year is not a unit of time, but of distance, an immense one. It equals approximately 9.46 trillion kilometres, a number so large that if you tried to count every kilometre, 1 per second, it would take you nearly 300,000 years just to finish counting. And this is where the true scale of the universe begins to overwhelm us. Our solar system, with all its grandeur, spans only about 2 light years, if we include the outer edge of the Oort cloud. But the moment you step beyond that boundary to reach the nearest star, Proxima Centauri, the distance jumps to 4.24 light years. Pause for a moment and think about that. The closest neighbouring star, the one sitting right next to us in our galactic neighbourhood, is so far away that light itself, the fastest thing in existence, needs more than 4 years to get there. If Proxima Centauri were to explode tonight, humanity would have to wait over 4 years just to see the light from that event reach our eyes. When we look deep into space, we are not seeing the present. We are looking into the past. This is one of the most important insights in modern astronomy. The night sky is not a snapshot of the present moment. It is a layered record of history. Some of the stars you see shining may have already died millions of years ago, their final light still travelling toward us. In space, distance is time. The farther away something is, the deeper into the past we are looking. Light becomes a messenger carrying ancient information. It does not just tell us where something is, it tells us what it looked like when our own world did not yet exist. At larger scales, the slowness of light becomes almost painful to comprehend. To cross the Milky Way, light requires about 100,000 years. To travel from the nearby Andromeda galaxy to us, it takes about 2.5 million years. In this vast universe, light, the very symbol of speed, begins to feel slow, like a traveller crossing an endless desert. Every piece of information we have about the universe is limited by the speed of light. We are like inhabitants of a distant island, receiving messages in bottles sent millions of years ago. There is a quiet loneliness in that realization. Even if another civilization existed just a few hundred light years away, and they sent us a signal right now, it would take centuries for it to reach us. The universe seems structured in a way that prevents instant communication, isolating each star system, each galaxy, into its own island within an ocean of time. Light gives us a way to measure the universe, but it also reveals the boundaries we cannot cross. It reminds us that no matter how far human knowledge advances, we are still bound by the rules of a universe far greater than ourselves. Look into the darkness between the stars, where light must travel for years, centuries, or even millions of years just to pass through. Can you truly imagine a distance so vast that even the fastest thing in the universe seems to age along the journey? And when you realize that every point of light above you is a portrait of the past, where do you feel you stand within this endless flow? The truth is, light does not only show us how big the universe is, it quietly warns us about something else. A journey between the stars that humanity may never truly be ready to take. And if light is our measuring tool, then is everything within its reach truly all that exists? We are about to move deeper into interstellar space, where the numbers begin to stretch beyond ordinary logic. Part 3. Interstellar space. Distances beyond intuition. As we leave behind the last icy remnants of the Oort cloud, we officially enter a new domain, interstellar space. This is a region of near total emptiness. There is no sunlight to provide warmth, no atmosphere, and almost no significant matter. Only the quiet presence of sparse hydrogen atoms drifting across distances that the human mind evolved to navigate just a few kilometers simply cannot grasp intuitively. To understand the severity of interstellar distances, consider Voyager 1. Launched in 1977, it remains the farthest human-made object in history. It is travelling at over 60,000 kilometers per hour, a speed that, on Earth, could take you from Hanoi to London in under 10 minutes. And yet, after nearly 50 years of uninterrupted travel, Voyager 1 is still only just beyond the edge of our solar system. If its destination were the nearest star system, Alpha Centauri, it would require another 70,000 years to arrive. 70,000 years. That is roughly 14 times the entirety of recorded human civilization. By the time such a journey is completed, humanity may have evolved into something entirely different, or perhaps no longer exist at all. This reveals a crucial insight. The greatest barrier we face is not propulsion technology, but time itself. The universe appears to impose a kind of isolation on intelligent civilizations. The average distance between stars in the Milky Way is about 5 light years. Imagine attempting to send a simple "hello" message to a civilization on the opposite side of the galaxy using radio waves, which travel at the speed of light. That message would take 100,000 years to arrive, and if they replied immediately, you would wait another 100,000 years to receive the response. From the Stone Age to the age of artificial intelligence, the entire arc of human history is just a brief moment compared to the time required for a message to cross the galaxy. Even if the Milky Way were filled with intelligent life, each civilization would remain effectively isolated, confined within its own star system by invisible, unbreakable barriers of time. Interstellar space is not a road, it is a vast, dark ocean, where each star is a distant island separated by trillions of miles. This emptiness is so extreme that even when galaxies collide, the chance of two stars actually crashing into one another is nearly zero. They simply pass through each other, like ghosts drifting across an empty stadium. This sparsity protects us, but it also confines us. We stand on a small grain of dust, looking outward and dreaming of journeys to distant worlds. Yet the reality of physics reminds us that crossing interstellar space requires more than faster ships. It may demand an entirely new understanding of space and time. As we move deeper into this void, every concept of near and far begins to collapse. Here, even a light year becomes just a small marking on an endless scale. We are drifting within a reality where silence is not merely the absence of sound, but the absence of presence itself. And in this vast darkness of interstellar space, where even light must travel for years to reach its next destination, do you believe that a human life barely lasting a century could ever truly complete an interstellar journey? Or are we meant to remain distant observers, watching those shining islands through telescopes, accepting our place as solitary witnesses? The truth may make us feel small, but recognizing these distances beyond intuition, is the beginning of a deeper understanding of the universe. Because what we have just encountered is only the first layer of isolation, and beyond it lies something even larger, the true structure of the immense system we call the Milky Way. Part 4. The Milky Way, a vast home in the dance of gravity. If the journey through interstellar space left us feeling isolated in darkness, then in this chapter we begin to realize something very different. We have never truly been alone. We are part of a vast, luminous city, more vibrant and dynamic than anything the human mind can easily imagine. Welcome to the Milky Way, a colossal home that holds the entire history, breadth, and future of humanity. From Earth, on quiet, dark nights, the Milky Way appears as a faint, misty band stretching across the sky. But if we could step outside and look back at it from afar, that band would transform into a magnificent spiral of light and dust. The Milky Way is a barred spiral galaxy, a vast, disk-like structure spanning about 100,000 light-years in diameter. To put that into perspective, if our entire solar system were reduced to the size of a coin, the Milky Way would be as large as a continent. Within this continent of light, there are not just millions or billions, but between 100 and 400 billion stars. Each one is a sun, and data, as of 2026, suggests that most of them host at least one orbiting planet. That means there could be trillions of worlds scattered across these spiral arms, waiting silently to be discovered. There is a simple truth that our intuition often fails to grasp. You are never truly standing still. At this very moment, as you sit or lie quietly listening, you are part of an extraordinary motion. The Earth orbits the Sun, but the Sun itself, along with all of us, is being carried along in a much larger flow. The entire solar system is moving through space at an astonishing speed of about 220 kilometers per second. At that speed, we are traveling over 800 times faster than a commercial jet. Every second, you move the equivalent distance from Hanoi to Vinh. Every minute, more than 13,000 kilometers pass beneath you, unnoticed. We are participating in a vast cosmic dance around the center of the galaxy, a journey astronomers call a galactic year. To complete just one orbit around the Milky Way's center, the Sun takes about 225 million years. The last time Earth occupied this exact position in space, early dinosaurs had only just begun to appear. Humanity did not yet exist. We are travelers aboard a massive rotating system, a vessel called the Milky Way. So what holds all of this together? What keeps hundreds of billions of stars from drifting into the endless void? The answer lies at the heart of the galaxy. At its center, Hidden behind dense clouds of dust that visible light cannot penetrate, lies Sagittarius A star, a supermassive black hole with a mass about 4 million times that of our Sun. But this black hole is not a devouring monster, as often portrayed in fiction. It acts more like a gravitational anchor, shaping the structure of the entire galaxy. Around it, stars move at incredible speeds, thousands of kilometers per second, creating a region that is both brilliant and chaotic. We are fortunate to be located far from that center, in a relatively calm region known as the Orion Arm, about 26,000 light-years away. Far enough to remain safe, yet close enough to be part of this immense system. When we look at the Milky Way, we begin to see a remarkable hierarchy. Earth is a grain of sand within the solar system. The solar system is a faint point within the Orion Arm, and the Orion Arm is just a small segment of the galaxy's sprawling spiral structure. Most of the stars you see in the night sky belong to a small local bubble surrounding us, less than 1% of the galaxy's total size. The rest of the Milky Way remains distant and largely unseen, obscured by dust and vast distances that even light struggles to cross. The Milky Way is not just a static structure, it is a cycle of continuous transformation. In the spiral arms, clouds of gas collapse under gravity to form new stars. Elsewhere, aging stars explode as supernovae, scattering elements like carbon, iron, and calcium into space, the very materials that would one day form planets, and eventually, life itself. We do not merely live in the Milky Way, we are made from it. Pause for a moment and feel this. Close your eyes if you wish, and imagine the massive planet beneath you moving at 220 kilometers per second through the darkness of the galaxy. Why do you not feel it? Why does everything around you remain still? The cup on your table unmoved, your breath steady and calm. Is it because we are too small to perceive the storm we are part of? Or because the universe operates with such precision that even the most immense motion becomes a form of perfect stillness? And yet, even something as vast as the Milky Way is only a small island. When we look beyond its edges, we begin to see other enormous shapes drifting in the darkness. Other galaxies, waiting. Some of them are so large, they seem capable of overwhelming even our imagination. Part 5. Other galaxies, when greatness becomes ordinary. As we leave behind the luminous spiral arms of the Milky Way and move toward its outer boundary, the darkness begins to feel different, deeper, more absolute. This is no longer the darkness between stars, but intergalactic space, a vast abyss where matter is so sparse that it approaches near-perfect vacuum. Looking back, our Milky Way now appears as a solitary whirl of light. But as your gaze stretches farther into the distance, a striking realization begins to emerge. The universe is not empty. It is an ocean filled with countless islands of light, much like our own home. The first major structure we encounter in this darkness is Andromeda Galaxy. Located about 2.5 million light-years away, it is the largest spiral galaxy in our local region. Data up to 2026 suggests that Andromeda is not only larger in size, but may contain up to 1 trillion stars, 2 to 3 times more than the Milky Way. Despite the immense distance, if it were bright enough, Andromeda would appear in our night sky as an object 6 times wider than the full moon. And yet, there is something even more dramatic unfolding. The Milky Way and Andromeda are moving toward each other at a speed of about 110 kilometers per second. In roughly 4 billion years, these two giants will merge, forming a new, larger galaxy. We are not just observers of this process. We are participants in a vast intergalactic gravitational dance. If Andromeda makes the Milky Way seem modest, then there are structures beyond that make even Andromeda feel small. Far in the direction of the Virgo constellation lies one of the largest galaxies ever observed, IC 1101. IC 1101 is a supergiant elliptical galaxy with a diameter of about 6 million light-years. To understand its scale, if it replaced the Milky Way, it would engulf Andromeda, the Triangulum galaxy, and all the space in between. It contains an estimated 100 trillion stars, a number so large that it stretches beyond ordinary comprehension. If each star were a grain of sand, IC 1101 would hold enough to fill an entire stadium, while the Milky Way would be just a small handful in comparison. It is a realm of ancient stars, dim, red, and aging, where star formation has long since slowed, giving way to a quiet, immense grandeur. But the universe is not limited to spirals and spheres. There are irregular galaxies, distorted by past collisions, and dwarf galaxies containing only a few million stars, drifting like satellites around larger systems. By 2026, observations from next-generation space telescopes have revealed something even more subtle. Even regions once thought to be empty contain thousands of faint galaxies. They resemble particles of dust illuminated by a beam of light in a dark room. Each tiny glow represents billions of stars, billions of planetary systems, and perhaps billions of untold stories. For centuries, humanity has held on to the belief that we are special. We once believed we were at the center of the solar system, then at the center of the galaxy, and perhaps even the universe itself. But when we look out at the vast population of galaxies, from the smallest dwarfs to giants like IC 1101, we begin to understand something deeper. The Milky Way is an average galaxy. It is not exceptionally large, nor particularly small, not unusually bright, nor especially faint. It is typical. We exist in what could be described as a common neighborhood of the universe. The grandeur of the Milky Way that once overwhelmed us now becomes a reference point, a midpoint on the scale of intergalactic space. And within this immense ocean filled with luminous islands, where each galaxy may contain trillions of opportunities for life, have you ever considered that the place you call home, the Milky Way itself, might simply be ordinary? Does that realization feel unsettling? Or does it bring a sense of quiet comfort, that we do not need to be at the center to have meaning, that even in our ordinariness we remain part of something vast, something alive, expanding and interconnected? Because that very sense of ordinary is not the end of the journey. It is the doorway to something even larger, a structure where galaxies themselves are no longer isolated, but connected into immense cosmic cities. And that is where we are going next, into the domain of superclusters. Part 6. Large-scale structure, the cosmic megacities. As we move beyond the isolation of individual galaxies, a deeper pattern begins to reveal itself, a fundamental rule of the universe. Everything tends to gather. Just as humans form villages, and villages grow into cities, galaxies are not scattered randomly. They are bound together by an invisible yet powerful force: gravity. Welcome to the next level of scale, where we no longer count stars, but entire collections of galaxies. Let us begin with our own neighborhood. Astronomers call it the local group. It is a modest collection of around 80 galaxies. Within it, the Milky Way and the Andromeda Galaxy are the dominant giants, while smaller dwarf galaxies orbit around them like satellites. The local group spans roughly 10 million light-years, an immense distance by any human standard, yet on the cosmic map, it is little more than a quiet suburb at the edge of something far larger. If the local group is a neighborhood, then about 50 million light-years away, we encounter something closer to a true cosmic city, the Virgo cluster. This is a region dominated by gravity. The Virgo cluster contains between 1,300 and 2,000 galaxies, packed into a relatively dense volume of space. At its center lies massive elliptical galaxies such as M87, home to the first supermassive black hole ever directly imaged by humanity. The gravitational pull here is so strong that it is drawing our local group toward it. We, along with dozens of other galaxy groups, are effectively satellites orbiting this luminous, massive structure. But even the Virgo cluster is only a fragment of something far greater, something that humanity has only begun to map in recent years. Thanks to increasingly precise measurements of galaxy motion, refined up to 2026, we can now identify the broader structure that we truly belong to. It is called the Laniakea supercluster. In Hawaiian, Laniakea means immense heaven. Unlike a simple sphere or disk, Laniakea resembles a vast network of flowing filaments, threads of light stretching across space. converging toward a shared gravitational center. It contains the local group, the Virgo cluster, and hundreds of other galaxy clusters, all woven together into a single system. Pause for a moment and take in this number. Laniakea spans approximately 520 million light-years. For light, the fastest entity in the universe, to travel from one end to the other, it would take more than 500 million years. This means that if an event were happening right now on the far edge of Laniakea, by the time its light reached Earth, our planet might have undergone multiple cycles of extinction and evolution. At this scale, the idea of the present begins to lose meaning. We are only ever seeing echoes of the distant past. Within Laniakea, everything is moving with direction and purpose. Like water flowing downhill, hundreds of thousands of galaxies are gradually being pulled toward a mysterious region known as the Great Attractor. This is a massive concentration of matter, hidden behind dense cosmic dust within our own Milky Way, making it difficult to observe directly. Yet its influence is undeniable. It is shaping the motion of the entire supercluster. Our cosmic home is drifting along a vast gravitational current toward a destination we are only beginning to understand. At this point, a profound realization emerges. The universe is not chaotic. It is structured. Planets orbit stars. Stars gather into galaxies. Galaxies form groups and clusters. Clusters connect into superclusters. Each level introduces new laws, new distances, and new scales that surpass anything our ancestors could have imagined. We do not simply live on a planet. We exist within a layered structure, a vast interconnected network where every component is linked. Pause. Take a breath. Imagine standing at the highest possible vantage point, looking down at the entirety of Laniakea, a field of over 100,000 galaxies, shimmering like droplets of light across a cosmic web. Can you truly comprehend a structure so large that light itself needs hundreds of millions of years just to cross it? When you hear a number like 520 million light-years, does your sense of space begin to shift? Do you feel smaller, almost fading into insignificance? Or do you feel something else, a quiet sense of wonder that your mind is capable of even beginning to grasp a structure this vast? And yet, Laniakea is not the end. Beyond it, other superclusters stretch across the darkness, and they do not stand alone. They connect, forming something even greater, a structure that defines the universe itself, the cosmic web. Part 7. The cosmic web, the grand network of the universe. When we step back far enough beyond even the luminous boundaries of the Laniakea supercluster, a striking truth begins to emerge. At the largest scales we can observe, the universe is not a random scattering of galaxies. It is not a chaotic fog drifting in darkness. Instead, the universe has an architecture, a structure so intricate, interconnected, and breathtaking that scientists call it the cosmic web. If you could rise above everything and look down on the universe as a whole, you might see something resembling the neural network of the human brain, or delicate strands of a spider's web shimmering in morning light. This network is woven from two opposing yet inseparable components, filaments and voids. Filaments are vast cosmic highways, dense with gas and billions of galaxies. They are the regions where matter gathers, where light shines brightest. These strands stretch across unimaginable distances, connecting galaxy clusters and superclusters into a single, continuous framework. Between these filaments lie the voids, enormous bubbles of emptiness. Some span hundreds of millions of light-years, containing almost no stars, no galaxies, not even dust. They are the deserts of the universe, occupying most of its volume while holding the least amount of matter. Why does the universe arrange itself this way? Why not distribute matter evenly? The answer takes us back to the earliest moments after the Big Bang. Observations and simulations from organizations like NASA, combined with data from the Euclid Space Telescope updated through 2026, reveal that the cosmic web formed from a long, ongoing tension between expansion and gravity. In the early universe, certain regions contained slightly more matter than others. Gravity amplified these differences, pulling more material into denser areas over billions of years. As matter gathered into filaments, vast, empty regions were left behind, forming the voids. But this network is not static. It is alive, in motion. Gas flows along filaments like blood through veins, feeding galaxy clusters at their intersections. These nodes, where filaments meet, become centers of intense activity, where new stars are born and galaxies evolve. The deepest insight offered by the cosmic web is this: the universe is not random. From subatomic particles to structures spanning billions of light years, everything follows consistent physical laws. Matter is distributed with order, not chaos. When scientists map the cosmic web and compare it to neural structures, an unexpected similarity appears. It is as if the universe is organized with a kind of efficiency, where every galaxy is a node, every void a pause in a larger cosmic rhythm. By 2026, astronomers have even begun to directly observe faint, diffuse gas connecting galaxies, structures once predicted only by simulations. These discoveries confirm that the universe truly is a vast, interconnected system, a kind of cosmic body in which we are only a tiny, almost invisible part. Take a moment and expand your imagination just a little further. Imagine standing outside this network, looking at trillions of galaxies glowing along endless strands of light. Do you believe this precise arrangement is the result of random collisions over billions of years? Or does it suggest an underlying order we are only beginning to understand? And when you notice the resemblance between this cosmic network and the neural pathways within your own mind, do you feel a connection? Could the universe be something more than a collection of objects? Something closer to a system, a structure, perhaps even a form of existence beyond what we can define? And yet, for all its vastness, even the cosmic web has a limit. It is the boundary of what we are able to observe. Beyond the luminous threads of this network lies a concept that begins to challenge everything we think we know about space and time, the observable universe. And that is where we are going next. Into a realm where the edge of reality itself slowly comes into view. Part 8. The observable universe, the edge of reality and the past. After passing through the vast filaments of the cosmic web, we arrive at a boundary where every familiar idea of distance begins to bend under the weight of time. This is the farthest limit human understanding can reach, the observable universe. By 2026, thanks to breakthroughs from the James Webb Space Telescope and next-generation infrared observatories, we are not only seeing farther, but also seeing earlier than ever before. And yet, this journey reveals something unsettling. The universe is far larger than what light allows us to observe. Let us begin with a number that often confuses even the most logical minds. We know the universe is about 13.8 billion years old. Based on simple reasoning, the farthest object we should be able to see ought to be 13.8 billion light-years away. But reality is different. The diameter of the observable universe is about 93 billion light-years. Why does this contradiction exist? Because the universe is not static. During the 13.8 billion years that light has been travelling toward us, space itself has been expanding. The galaxies that emitted that light, when the universe was young, have since been pushed much farther away. Today, they lie roughly 46.5 billion light-years from us in every direction. This means that when you look at the deepest images captured by James Webb in 2026, you are seeing galaxies that at this very moment exist far beyond the reach of any signal we could ever send. We can see them, but we can never reach them. Within this immense sphere, 93 billion light-years across, scientists estimate there are about 2 trillion galaxies. Take a moment and try to grasp that number, 2 trillion. If each galaxy were a single sheet of paper, the stack would stretch from Earth to the Moon, and back again, dozens of times. And within each of those galaxies are hundreds of billions of stars, each one potentially hosting its own planetary system. In its latest observations, The James Webb telescope has even detected galaxies that seem to appear too early. Massive, luminous structures that formed just a few 100 million years after the Big Bang. These are like fossils of light, evidence of how rapidly and intensely the universe began to shine in its earliest moments. This leads to one of the most important insights of all. In the universe, looking farther means looking deeper into the past. When you look at the moon, you see it as it was 1 second ago. When you look at the sun, you see it as it was 8 minutes ago. When you observe stars in the Milky Way, you see them as they were thousands of years ago. And when we use powerful telescopes to reach the edge of the observable universe, we are witnessing the universe just as it was in its earliest stages. The observable universe is like a vast museum, where every exhibit is made of light. At its outermost boundary lies the cosmic microwave background, the faint afterglow of the Big Bang. It is the final wall of observation. Beyond it is a region of darkness, where light has not yet reached us, or where space itself is expanding so rapidly that those regions are forever beyond our sight. We live inside a bubble of light. With every passing second, light from more distant regions reaches us, expanding this bubble slightly. But at the same time, the accelerated expansion of the universe is pushing galaxies away, faster than light can bring their signals back. At some point in the far future, all galaxies beyond our local group will disappear from the sky. Future civilizations will look up and see only darkness, never knowing that a universe filled with 2 trillion galaxies once surrounded them. We are living in a rare moment, a moment when the universe is old enough to have formed intelligent life, yet young enough for us to still observe its history. Pause for a moment and look into the dark space between the stars. Do you realize that you are not truly looking into space, but into history? Every photon reaching your eyes right now may have begun its journey billions of years ago, traveling across vast cosmic structures just to carry a message from the past. When you understand that you stand at the center of a sphere containing 2 trillion galaxies, and that every second you breathe, new light from the most distant regions is arriving, do you feel the weight of that presence? We are, in a very real sense, time travelers through observation. And yet, everything we have just seen, those trillions of stars and galaxies, may only be a small fraction of what truly exists, because the most dominant component of the universe is something we cannot see at all. Now, we begin to face the darkness. Part 9. Dark Matter and Dark Energy. The Rule of the Invisible Darkness. We have come a long way together, from grains of sand on Earth, through radiant megacities of galaxies, all the way to the edge of the observable universe. By now, you may feel overwhelmed by the sheer scale of trillions of galaxies shimmering in the distance. But this is the moment we must face one of the most shocking truths in modern science, a truth that can challenge everything you trust your eyes to see. Everything we have just explored, the sun, the planets, billions of stars, magnificent spiral galaxies, and even your own body, represents only a tiny fraction of the universe. All of it accounts for just about 5%. Imagine watching a puppet show. You see the figures moving gracefully on stage, but you cannot see the strings controlling them, nor the hands behind the curtain. That is how we discovered dark matter. From the late 20th century to the most precise observations up to 2026, especially from missions like the Euclid Space Telescope, scientists noticed something unusual. Galaxies are rotating too fast. Based on the visible matter we can observe, gravity should not be strong enough to hold them together. The stars should have flown apart long ago. Something unseen, massive, and invisible must be surrounding these galaxies, providing the extra gravitational pull needed to keep them intact. This substance does not emit light, absorb light, or reflect light. It passes through your body, through the Earth itself, like a ghost. Dark matter makes up about 27% of the universe. It is the invisible framework, the scaffolding, on which galaxies are built. Without it, the cosmic web we explored earlier would collapse, and the conditions necessary for life would never have emerged. If dark matter is the glue that holds the universe together, then on larger scales there is an even more powerful force pulling everything apart. This is known as dark energy. In 1998, scientists made a startling discovery. The universe is not only expanding, the expansion is accelerating. Some unknown form of energy is pushing galaxies away from each other faster and faster. Unlike matter, this energy does not gather in one place. It exists everywhere, embedded in the very fabric of space itself. The more space expands, the more dark energy there is to drive that expansion further. As of the most accurate measurements in 2026, dark energy accounts for about 68% of the total energy density of the universe. It is the dominant force shaping cosmic evolution, gradually overpowering gravity and driving the universe toward a future of increasing isolation. At this point, we must shift our perspective. We are used to believing that seeing is believing, but in the universe, what we see is only the surface of a much deeper, darker ocean. The ordinary matter that forms stars, planets, and life is just a small deviation, a minor fluctuation in the total energy of existence. We live in a universe governed by invisible forces. Dark matter builds the structure, dark energy stretches it apart. And as of 2026, science is still searching for the true nature of these two dominant components. We know they exist through their effects on light and motion, but we have never directly touched them. The universe continues to hide its deepest secrets in absolute darkness. Look at your hand for a moment, then look out into the space beyond your window. Everything feels solid, real, certain. But right now, billions of dark matter particles may be passing through every cell of your body, and you would never notice. And the empty space between you and the stars may be filled with an energy so powerful it can pull apart even the largest superclusters over time. If 95% of the universe is invisible, and your senses can only perceive the remaining 5%, can you still trust what you see? Or is the reality we experience only a thin layer floating above something far greater and far more unfamiliar? When we begin to understand the dominance of this invisible darkness, we no longer see ourselves as the center of the universe. We become something else. Observers, visitors, trying to read a book where most of the pages are written in invisible ink. And yet, it is this darkness that leads us to the final question. Where does this journey go next? Does the universe have a limit? And what kind of future lies beyond the horizon we cannot see? Part 10. Limits and the Future. Ghosts on the Horizon. Our journey has taken us from grains of dust in the palm of a hand to the outer edge of the largest structures the human mind can comprehend. But at this final stop, we are no longer looking at what exists. We are looking at what will be lost. This is the closing chapter of a cosmic story, where we confront the ultimate limits of physics and the long-term fate of everything that exists. The universe is not only vast, it is changing in a way that no future technology may ever reverse. We often imagine a distant future where humanity explores faraway galaxies, but there is a fundamental barrier known as the cosmic horizon. It is not a visible wall, but a limit defined by speed and time. As we have seen, dark energy is driving galaxies apart at an accelerating rate. At a certain point, the distance between us and distant galaxies will increase faster than light can travel. And this leads to a profound consequence. Light from those galaxies will never reach us again. They will slip beyond our observable horizon, like ships disappearing over the edge of an ocean. Even if you had a telescope 1 billion times more powerful than the James Webb Space Telescope, you would see nothing but darkness in their direction. The galaxies you see in NASA images today, as of 2026, are already on their way out of reach. Modern physics teaches us something difficult to accept. The limits of humanity are defined by physics, not by technology. Even if, millions of years from now, humanity develops engines capable of bending space itself, we may never outrun the expansion of that space. The universe is gradually pulling itself apart. Within about 100 billion years, all galaxies beyond our local group will disappear completely from view. The night sky of distant descendants will be different. They will see only a few faint points of light, remnants of nearby galaxies that have merged. To them, the universe will appear small, quiet, and empty. They will never know that in 2026, their ancestors once observed a vast cosmic web filled with trillions of galaxies. We are living with a rare privilege, one that time will eventually take away. The far future of the universe unfolds across eras so immense that ordinary measures of time lose meaning. The stelliferous era, the age of stars, is the one we live in now. It is a time when stars continue to form and shine, but it will come to an end in about 100 trillion years, when the last reserves of hydrogen are exhausted. The final stars will fade, like candles slowly going out in an ever-expanding darkness. After that comes the degenerate era, where only the remnants of stars remain: white dwarfs, neutron stars, and black holes. Then, the black hole era. At this stage, black holes become the dominant structures in the universe, but even they are not eternal. According to Hawking radiation theory, black holes slowly lose mass and eventually evaporate. After approximately 1 everything we have explored in this journey would be gone, unseen, unknown, perhaps even unimaginable. Every image returned by the James Webb telescope, every number we measure, is something time is slowly taking away. When you consider the scale and fate of the universe, does each moment begin to feel more significant? Every second you are alive, every photon reaching your eyes, carries information from across vast stretches of space and time. The universe may be too large to fully comprehend, but it is still generous enough to reveal its beauty to us before the darkness closes in. And for now, we are here to witness it. Our journey, from tiny grains of dust to the edge of the observable universe, comes to a gentle pause here. Many people say that when they look at the vastness of 2 trillion galaxies, or the cosmic web stretching across billions of light years, they feel small, even insignificant. But Space Lull invites you to see it differently. You are not small. You are simply looking at something immensely large. In truth, you are a remarkable outcome of probability. For you to be here, listening, reflecting, and contemplating the scale of the universe, it took about 13.8 billion years for the cosmos to forge the atoms within your body. You are not separate from the universe, observing it from the outside. You are a part of the universe, becoming aware of itself. The calcium in your bones, the iron in your blood, were created in the final moments of massive stars. Those elements have gathered over time to form something extraordinary: your consciousness. We are living in one of the rarest and most precious moments in the history of existence. A moment when light still travels freely enough to tell the story of the past, and space has not yet expanded so far that it hides the distant neighbours from view. You are among the few beings granted this privilege, to see and to understand. Now, allow your body to relax. Let the billions of years, the superclusters, and the invisible darkness slowly drift into the background. The universe remains out there, vast, quiet, and precise, unfolding in a way that has allowed life to exist safely on this small blue planet. If you are still here, listening to these final words, Space Lull would like to offer you a sincere thank you. In a world that moves so quickly, thank you for taking this moment to slow down, to reflect, and to appreciate the quiet beauty of existence. Before you drift into sleep or return to your day, would you share something with us? Where are you listening from on this earth? And what time is it right now where you are? Leave a comment, a small signal, a quiet greeting between fellow travellers in this vast ocean of space. Wishing you a peaceful rest and dreams that reach beyond the horizon of the universe. Good night, and we'll meet again in the next journey with Space Lull.